At the end of our last lesson, we introduced Fermat's right triangle theorem. And this is the only result of Fermat that we know he had a proof of. Since for the rest of the statements, we just have the marginal notes, but there is no proof attached to them. And so, of course, it's still possible that Fermat had proven some of his other marginal notes, but did not write those proofs down in the margin like he did with the right triangle theorem. But given that some of these statements were incorrect, a strong argument is to be made that Fermat had no proofs for many of his statements and instead had come to them by computational example and then giving a generalization that this should hold true because it seems to hold for some cases. And so that's one of the consensus regarding Fermat. And Euler, as we have seen in this course, he proved Fermat's little theorem, he proved the sum of squares theorem, and he devoted a considerable, he devoted his lifetime to settling the open statements that at the time were still open from Fermat. Another mathematician we have not spoken about is Bernard Frenicle de Bessy, who is amongst the first to start working on statements that Fermat claimed to have proven and settling them. So for context, Fermat's right triangle theorem, the proof that is written here that you will be investigating as part of your last homework assignment, that was written in the marginal note dated 1641. Fermat would not pass until 24 years later. After Fermat's passing in 1665, his son would later publish a new edition of Diophantus's Arithmetica with the marginal notes that his father had made throughout his lifetime. And these are the famous marginal notes that led to Fermat's last theorem being called the last theorem, since it was the last of these marginal notes to be proven. Now, with Fermat's last theorem, we have the n equals to 4 case, which is usually associated to Fermat since it is an easy consequence of the right triangle theorem, and so the agreed upon view amongst math historians is Fermat most likely had a proof since it is an easy consequence. But the proof, the first actual proof of it would not come until 1676 when de Bessy utilized Fermat's right triangle theorem to deduce the n equals 4 case of Fermat's last theorem. But as we will see, the proof is essentially automatic if we assume the right triangle theorem. And so for those reasons, it is easy to speculate that Fermat did in fact have a proof in the case when n is equal to 4. So now let us go ahead and follow in the footsteps of de Bessy and prove Fermat's last theorem in the n equals to 4 case. And so here's the argument. So we're going to go by contradiction. So we're going to suppose that x, y, and z are natural numbers with x to the 4 plus y to the 4th equals z to the 4th. And let's go ahead and let d be the GCD of x and y. Then we have that x over d, quantity to the 4 plus y over d, quantity to the 4th is equal to z to the over d, quantity to the 4th. So we're going to have this here. In particular, we have another solution to Fermat's last theorem in the n equals to 4 case. And so we may assume that the GCD of x and y is equal to 1 after relabeling, since the GCD of x over d, y over d is equal to 1. So all we are doing is we start off with a solution to Fermat's last theorem. If we have one, we divide by the GCD of x and y, and we get another solution to Fermat's last theorem because x over d to the 4th plus y over d to the 4th is going to equal y over d, z over d to the 4th. And x over d and y over d are relatively prime, So if we need to relabel, we can go ahead and do that. And that will give us a solution to Fermat's theorem with now the x, y, and z being relatively prime. And that's what we're doing now. And so we're going to go ahead and assume that the GCD of x and y is 1. So as a consequence, we have that x to the fourth, x squared, y squared, and z squared is a primitive Pythagorean triple. And now let's go ahead and remind ourselves that in the original marginal note that Fermat wrote down for Fermat's theorem, it was written right next to the Pythagorean triple theorem of Diophantus. And so in Arithmetica, that is where the famous marginal note lies, is with this statement. And so this is something that was well known to Fermat. And so it is, as we will see, the proof of this is not so, it's going to be quite easy corollary of Fermat's right triangle theorem. And so it's easy to see that this is something that he could have easily devised. And so now we are going to go ahead, apply the Pythagorean triple theorem. We have a primitive Pythagorean triple. So that means that x squared has to be 2pq, y squared equals p squared minus q squared, and then z squared is equal to this. Of course, we may have to relabel, change x and y, because one of these has to be even. We don't know which. And so relabeling if necessary. So specifically, so we have theorem. So this is the Pythagorean triple theorem. We have by theorem 124.2, there exists natural numbers p and q with p greater than q, such that after relabeling if necessary, we have that x squared is going to be equal to 2 times pq, y squared is going to be equal to p squared minus q squared, and z squared is going to be equal to p squared plus q squared. But this is the amazing part of this proof. At this stage, we're almost done, because we have another Pythagorean triple right here. And what I forgot to write down is, of course, that p and q are relatively prime. So that is something that we need. And so we have GCD of p and q is equal to 1. So we have that from the Pythagorean triple theorem. So we know that the p and q are relatively prime. So note that p, q, and z is a primitive Pythagorean triple. So in particular, we have a triangle. Having sides P, Q, and Z. And where Z, of course, here is the hypotenuse. So if we were to draw a triangle, we have one side will be P, one side will be Q, and then we have Z. What is the area of this triangle? 1/2 base times height. So the area of this triangle is 1/2 base times height, which is going to be 1/2 P times Q. So we have this here. But now let's go ahead and substitute in for PQ, because we know that PQ is equal to x squared over 2. So we have x squared over 2 is equal to P times Q. So this here is x squared over 4, which is equal to x over 2 quantity squared. So the area of the triangle is a square, which is our desired contradiction. And so this contradicts Fermat's right triangle theorem. And we are done. And just like that, we got the proof of the n equals to 4 case. And because of the argument being as simple as that, in terms of it being a consequence of the right triangle theorem, it is commonly accepted that Fermat did have a proof of this statement, even though he did not write it down. But the honor of the first proof will go to de Vesey, since he was the first one to publish a result, and it was based off the same argument we just did, basing it off Fermat's right triangle theorem, which was in the margin notes. And so the n equals to 4 case was actually one of the first statements of Fermat's margin notes that was settled. And so de Vesey did this along with other arguments of other claims that Fermat did. But Euler, almost a century later, would go on to find another proof of Fermat's last theorem in the n equals to 4 case, which did not rely on the right triangle theorem. So we are about to go ahead and prove the n equals to 4 case of Fermat's last theorem in a different way. And as you work through the right triangle theorem, what I want you to do is come back to the proof we are about to do for Euler. Because while our proof is the next proof is going to differ from this one here, the argument that Euler employed is very similar to the argument that is found in proving the right triangle theorem that you will be doing for homework via the guided exercises. Namely, it relies on the idea of infinite descent. But before we move on from Fermat and pass on to Euler, let me go ahead and give credit where it's due. I spent the last 8 weeks of the course attacking Fermat and saying that he did not write anything down, which is for the most part true, aside from the right triangle theorem. But one thing that is commonly not known about Fermat is that the area of math where he did contribute a lot, his name does not pop up. Whereas in number theory, as we have seen throughout our course, he is considered one of the founders of the modern theory by virtue of stating these marginal notes that led to many developments in the centuries that followed. But Fermat was one step ahead of Descartes. Descartes published La Géométrie, which merged geometry and algebra in 1637. But Fermat, as early as 1628, had already developed a method of what we will call Cartesian coordinates. But again, he was not an academic. He was working on his own, but he still collaborated. And so we know from his collaborations that not only did he discover the Cartesian coordinate system that we now use, but he also discovered the derivative. He was the one who came up with the difference quotient that we see in calculus. He was the one who came up with the integral. Well, there were other competing ideas for the integral, but he was the one who first showed that the integral of x to the n, specifically the integral from 0 to some real number a of x to the n, is equal to a to the n plus 1 over n plus 1. So the ideas that we see in calculus. And the ideas that he would write down in his correspondences will go on to influence mathematicians in the mid-1600s. And as we go forward into the 1660s, when a young Isaac Newton was at Cambridge, he took a course on what today would be called calculus. His professor, Isaac Barrow, in 1662 taught a course in which Newton was a student that brought the ideas of what we will now call calculus. Specifically, he was giving a course on the notion of these ideas that seem to be inverse of each other. The concept of the area below a curve, and the concept of taking the tangent to curves themselves, and that there was a relationship, and at that time it had already been proven for polynomials, what we now call the fundamental theorem of calculus. It was already known for polynomials, for functions that are trigonometric, but in special cases. And so Barrow's research was on generalizing this so that it extended to what we now will call differentiable functions. Barrow was also investigating how these ideas relate to physics, namely position, velocity, acceleration. And so when today we say that Newton discovered, Newton and Leibniz, that they discovered or invented calculus, that's actually completely wrong. What Newton and Leibniz did, amongst many other things, that gave them fame is prove the foremost conjecture of the time, what we now call the fundamental theorem of calculus. In Newton's writing, he even gives credit to Fermat, that his ideas that came into the fundamental theorem of calculus and its proof were based on Fermat's idea of tangent lines and the early work that he had done, since Barrow had been lecturing on those ideas. Actually, Newton was the top student in the course that Barrow gave him the task of typing up his notes for publication for the wider math community of the time. And so these are just these other aspects of Fermat that we have not talked upon, even though we have spoken about his work in number theory, where he essentially stated ideas that turned out in some cases to be right and lead to profound investigation. The branch of math where he had the most impact in actually doing things was analysis in its early foundations, and his name oftentimes is left out. And so let's go ahead now. We're going to move away from Fermat and now transition in our timeline for Fermat's theorem. So we're going to move forward back to Euler, whom we have covered in detail. And so Euler's work was actually an analysis early on. So he did his PhD in calculus and what we now call analysis. And he did not know, as he was working on his PhD, about Fermat's statements. It was not until Goldbach, in a letter in 1729, brought to Euler's attention the statement of Fermat's last theorem, amongst others. And these statements captivated Euler to the point that he became obsessed, as we have seen throughout our course, in proving the various statements that were still open at the time of Fermat. But even in the case of the n equals 4 case of Fermat's last theorem, Euler went about devising a new original proof of this result, which we are about to do. And so this is a proof of Euler due to that he published in 1738. So the proof that we are about to do is actually very similar in many ways to the one we just did, in the sense that we are going to go by contradiction, and then we are going to go ahead, use the fact that this is a primitive Pythagorean triple, use the Pythagorean triple theorem to write x squared, y squared, and z squared in this way. Where the proof differs is in by not using the right triangle theorem, we are not going to resort to this, but instead we're going to use the fact that P, Q, and Z is itself a Pythagorean triple and rewrite that once more using the Pythagorean triple theorem. And that's how we're going to get the contradiction, but we are building it upon the well-ordering principle. So let's go ahead and get started. So proof. As before, we're going to start off exactly the same. So towards a contradiction. Suppose there exist natural numbers x, y, z such that x to the 4 plus y to the 4 is equal to z to the 4th. In particular, and so here's where we use the well-ordering principle. So the set S, where this is the set of natural number C, such that there exists A and B natural numbers with GCD of AB1 and a to the fourth plus b to the fourth is equal to c squared. So that's our statement. And so this set is non-empty. Since we have that z squared over the GCD of a and b quantity squared is an s. And so here we're using the fact that if we divide, again, once as we did in the earlier proof, we divide by the GCD to the fourth, we're going to have x over the GCD to the fourth plus y over the GCD to the fourth is equal to z to the fourth over the GCD to the fourth. But now here we have a c squared. And so this is just, we're only looking at this now as a squared. And so we have this statement here. So that's our c. So by the Warr ordering principle, there is a least element. So next, we let z in S be the least element, and after relabeling, we have that there exists natural numbers x, y, x and y natural numbers relatively prime, such that we have that x to the fourth plus y to the fourth is equal to z squared. And so the key thing is that we have now done the relabeling, so we're still using x, y, and z, but this is not the same z that we started with since we changed the labeling. Because the original case was that z squared over the GCD's quantity squared was an s. And so now we have this here. But now we have a Pythagorean triple. So since we have that x squared, comma y squared, comma z is a primitive Pythagorean triple, we get that theorem, so the Pythagorean triple theorem. So theorem 1.24.2 asserts the existence of relatively prime, which I'm just going to abbreviate as REL, so relatively prime, P and Q in the naturals with P greater than Q, and we have that x squared is equal to, and after relabeling, after another relabeling, so this one I'm going to say possible relabeling, we have that x squared is equal to 2 times p times q, y squared is equal to p squared minus q squared, and z is equal to p squared plus q squared. So the reason for the relabeling over here in the phrasing is that it may be the case that our y is even. But when we use the Pythagorean triple theorem, we have to assert that x is even. And so we have to then interchange y and x, so that then x is even. And so that's the reason for this additional phrase right here. Okay, so now we have this. So now we're going to go ahead and focus on this side. And so this is where it differs from the right triangle theorem. So earlier, in our previous proof, we looked at z is equal to p squared plus q squared. And we applied, so in that case we had z squared. And so we applied the Pythagorean triple theorem to that. This time around, because we want to come back to our set S and get a contradiction with the minimality, we want to look at this quantity here. Since we also have a Pythagorean triple in this case, we have y squared plus q squared equals p squared. So next thing, so since the GCD of p and q is equal to 1, we have that p, q, and y are relatively prime, and thus we have that q, y, and p is a primitive Pythagorean triple. So here we're using again this here. We bring the q squared over, we have q squared plus y squared equals p squared. They are all relatively prime, so we have another Pythagorean triple. We are going to apply the Pythagorean triple theorem once more. So by theorem 1 to 4.2, there exists relatively prime natural numbers R and S. And I'm going to abbreviate relatively to REL again. So we have relatively prime natural numbers R and S with R greater than S. And after a possible relabeling, we get Q is equal to 2 RS, Y is equal to R squared minus S squared, and we get that P is equal to R squared plus S squared. So here we have just used the same exact statements that we had before. So we get these quantities right here. And now what we are going to do is come back to x squared is equal to 2 times p times q. And we're going to plug in q is equal to this. So observe that x squared, which is equal to 2 times p times q, is equal to 2 times p times q, which is now 2rs. So we get 4 PRS, which is the same. After dividing by 4 on both sides, we have x squared over 4 is equal to p times rs. So we get this here. But we also know that p, r, and s, since r and s are relatively prime, we have that p is relatively prime to r and s. So we deduce that P, R, and S are relatively prime. And now we're going to use the lemma from last time, so lemma 1.24.1. And so as a reminder, lemma 1.24.1 tells us that if we have that z to the n is equal to d times e, and all of these here are natural numbers, and we know that d and e are relatively prime, then d and e are perfect nth powers. In our case, we have something squared equals the product of 3 quantities, but we can generalize this and say that because they are all relatively prime, they all have to be perfect squares. So that's what we are going to apply now. And so by lemma 124.1, there exists relatively prime natural numbers a, b, c such that r is equal to a squared, s is equal to b squared, and p is equal to c squared. Now, so we have that r squared plus s squared is really just a to the 4 plus b to the 4. And now that is going to be, so we have r squared plus s squared. But if we come back over here, r squared plus s squared is equal to p. So we have that. That's equal to p, which in our case is equal to c squared. And this is what we want, because now that we have that c is an s. So we got our quantity c in here. And all that we need to do now is show that c is strictly less than our least element of s, which we chose to be z. And so now we just follow the inequalities. From here we have, so since we have z is greater than p squared, and that's just because here we're summing natural numbers, so p squared is definitely going to be less than z. So z is greater than p squared. But now c, p squared is equal to c to the 4th. So we got this here. And c to the 4th, since c is a natural number, we're going to have that that's going to be greater than c, which contradicts the minimality of z and s, which is our desired contradiction. And we have now finished Euler's proof of Fermat's last theorem in the n equals to 4 case. And as a consequence of this, of proving the n equals to 4 case of Fermat's last theorem, we actually get Fermat's last theorem for infinitely many exponents. Specifically, we have the following corollary. If n is a natural number, which is divisible by 4, then all the solutions to the Diophantine equation, x to the n plus y to the n equals z to the n, must satisfy x, y, z equals to 0. So let us go ahead and briefly prove this. So proof, if, actually, since 4 divides n, there exists some k in the naturals such that 4 times k is equal to n. And so if A, B, C is a solution to the Diophantine equation, x to the n plus y to the n equals z to the n, then a to the k b to the k, comma c to the k is a solution to the Diophantine equation x to the 4 plus y to the 4 equals z to the 4th. So we get this here. But we have already proven that there are no solutions in the natural numbers to this equation. So by theorem 124.5, it must be the case that we get the following. That a to the k b to the k times c to the k is equal to 0, which implies that a bc is equal to 0. And so we now have proven this here, because what we have now shown is the moment we have a solution to x to the n plus y to the n equals z to the n, where n is divisible by 4, we can go ahead, get this one right here. That's going to be a solution to this, but we already know what the solutions to x to the 4 plus y to the 4 is equal to z to the 4 are, and so we get what we want. And so we are done with this proof, and now we have Fermat's theorem for all exponents that are divisible by 4. And a similar argument allows us to prove that all we need to do now is look at the cases when p is a prime exponent. So let us go ahead and show this here, that it only depends on prime exponents. So here's the proof. So we're going to go by contradiction. Suppose Fermat's theorem is false. So then there exists natural numbers ABC such that a to the n plus b to the n equals c to the n for some n greater than or equal to 3. So now by the previous corollary, 124.6, we have that 4 does not divide n. So therefore, n is odd, or n is equal to 2 times k for some natural number k odd. So here k is odd. In either case, we have that n is divisible by an odd prime p. So now, there exists some natural number L such that n is equal to p times L. But then we have that a to the L, comma b to the L, comma c to the L is a solution to the Diophantine equation x to the p plus y to the p is equal to z to the p. But we are in trouble now, because our assumption is that if we have a solution to the Diophantine equation for some prime exponent, then the product of that solution must be equal to 0. So by assumption, and over here, of course, if we put a to the L inside here, that's going to be a to the L times p, which is n. So we're back to our assumption, our contradiction assumption. So in this case, we're now done. So by assumption, we get that a to the L, b to the L, c to the L, which is a, b, c to the L is equal to 0, which implies that one of a or b or c is equal to 0, which contradicts the fact that we chose these to be natural numbers. So now the lemma follows. So with this result, now we know that to prove Fermat's theorem, all we have to do is show it in the case when the exponent is an odd prime. If we show that for every single odd prime, then we have Fermat's theorem. But when was the case for p equals to 3 proven? After all, we have seen the n equals to 4 case. Fermat, as early as 1641, he could have proven the n equals to 4 case, but of course de Vesey is the first one who published a proof of the n equals to 4 case in 1676, and we saw his proof of that result using the right triangle theorem. Euler gave a new proof, which we just went over, that did not require the right triangle theorem, but that was not until 1738. But Euler being Euler, even though the n equals to 3 case up to that point had gone unsolved for now at that point a century, he went and started working on it, just like he did with the sum of squares theorem and its analogs. And the n equals to 3 case was considerably harder. It took him 15 years after his original proof of the n equals to 4 case in 1738. And so this came, due to Euler, in 1753. And in fact, we have the following quote that Euler, so shortly after proving the n equals to 3 case, Euler wrote to Goldbach to inform him that he had proven the n equals to 3 case. So here's the quote, and I'm paraphrasing the first part. I have proven the n equals to 3 case of Fermat's theorem. And then the actual translation of what follows says, the proof seemed very different from the proof of the n equals to 4 case, and that a proof of the general case still seemed remote. And what Euler was hitting upon were the ideas that would later lead to the proof of cubic and quartic reciprocity, namely looking at roots of unities. And so, if we have a natural number n, a root of the polynomial x to the n minus 1 is called an nth root of unity. And the problem is, since Euler essentially got upon this by chance in the sense that he was trying to prove Fermat's theorem and was working behind the scenes with the structure of this, it ended up being the case that this proof was wrong, unbeknownst to Euler. He would eventually indirectly fix it in his proof of the quadratic character of 2. And so we still credit Euler with having proven the n equals to 3 case as a byproduct of his work from 1770. And that settled the n equals to 3 case of Fermat's theorem. And so for those of you working on the project of the n equals to 3 case of Fermat's theorem, Edwards, Fermat's theorem, so the source, does go into detail as to why Euler's original proof was incorrect and how it can be patched to make it correct. But what is happening behind the scenes is really a question about the unique factorization when we are working with the roots of unity. So why was Euler wrong? And so to do that, let's go ahead and investigate what these numbers are, these roots of unities that we're calling. So we saw them earlier in a side discussion in an earlier lecture, but let's go ahead and formally introduce the roots of unity. So let's go ahead and think about the unit circle, but now the unit circle in the complex plane. And so here we have our imaginary axis. Over here we have our real axis. And the roots of unity are just going to be the points omega n, so that the angle that we make with the origin is theta. And the distance here is 1. So we're on the unit circle, so the distance to the point omega n is equal to 1. And we have this identity here. And so in the case of 4, so if we have omega sub 4, oh, and actually I should mention that this symbol here, that's lowercase omega, the Greek letter omega. So if we look at omega sub 4, what we have is e to the 2 pi I over 4, which by Euler's formula, which is actually not due to Euler but to de Moivre, we have that this is cosine of 2 pi over 4 plus I sine of 2 pi over 4. And this here is going to become cosine of pi over 2, which is going to be 0. And we have I sine of pi over 2, which is going to be 1. And so this is just I. So this is just to emphasize, 2 pi over 4, that's 90 degrees. So we should expect to get back I. So we have this here. In the case of Fermat's last theorem, if we have x to the 4 plus y to the 4 is equal to z to the 4, then we can write this as x to the 4 is equal to z to the 4 minus y to the 4th, which is equal to, by difference of squares, so z squared minus y squared, then z squared plus y squared. But z squared minus y squared is another difference of squares, so we have z minus y, z plus y, and then we have z plus iy times z minus iy. And we can write that succinctly as a product from j is equal to 0. Oops, not infinity. we definitely do not want to go to infinity. And here we have z minus omega sub 4 to the j times y. But notice that this factorization is happening over the Gaussian integers. So over the integers adjoint I, which in the new label it's omega sub 4. Since omega sub 4 is equal to I, so we have a way of factoring this. And you can actually prove Fermat's last theorem by using the fundamental theorem of arithmetic for the Gaussian integers, where now you have this quantity here is equal to a perfect fourth power. You can show that each of these ends up being relatively prime over the Gaussian integers, if we assume that there existed a solution, of course, to Fermat's last theorem. Each of these are relatively prime. And because they are relatively prime, an analog of the following statement that we showed earlier, the lemma 124.1, also holds over the Gaussian integers. That if you have Gaussian integers d and e that are relatively prime equal to a perfect nth power, then we have that d and e are both perfect nth powers. And so, because each of these ends up being relatively prime over the Gaussian integers, we have that this here being x to the 4th equals this product implies that each of these terms are perfect fourth powers. And so what Euler was doing in the process of proving n equals to 3 was something very similar. He was working with x cubed plus y cubed equals z cubed. So another contradiction argument here, so we're assuming that this exists. He factored it out as z cubed equals x cubed minus, oops, I meant to write x cubed. So we have x cubed is equal to z cubed minus y cubed. But now, this is going to be factored off as x minus y, then times x minus omega sub 3 y times x minus omega sub 3 squared times y. And so in other words, the product from 0 to 3 of x minus omega 3 y, and then omega 3 to the j. And omega 3 is going to correspond to the point that is going to be, so 2 pi over 3, which is going to be 120 degrees. And so we're going to have 120 and we're going to have a 240 for omega 3 quantity squared. And so this is how Euler went about proving the n equals to 3 cases, by considering this here. But the key thing to note is that this is before the language of rings was introduced. He was working with these ideas 150 years before they were formalized. And so what Euler did incorrectly in 1753 was in assuming that unique factorization held when we factored off this way. Because over the Gaussian integers, lemma 124.1 holds that we can say that each of these are perfect fourth powers. That is a byproduct that we have a fundamental theorem of arithmetic. So Euler didn't have that. So we can write the integers adjoin omega 3, and it turns out that this is the set of elements of the form a plus b, where now with b, we have omega 3, but we can write, it turns out that omega 3, after using Euler's formula, we have 1 plus root negative 3 over 2. And here a and b are integers. And so these are known as the Eisenstein integers. So we will not be studying these, but for historical purposes, this is the right ring to study for proving Fermat's last theorem in the n equals to 3 case. And what Euler failed to realize in his time, and we can't blame him given the tools that were available to him then, is that this here also has a unique factorization result. And by having unique factorization, then his proof holds true. But he did, as I mentioned, fix the proof indirectly by trying to do the quadratic character of 2, which would later set the stage for Eisenstein for the proof of quartic and cubic reciprocity, in which Eisenstein was studying rings like z adjoin omega 3 and z adjoin I, the Gaussian integers. And by working in those rings, Eisenstein proved these higher reciprocity laws. And so this is one instance where we see that Fermat's last theorem, in trying to solve this question, we start to understand a hidden structure that was up to that point unseen. Euler went about doing this factoring trick so that he can try to tackle Fermat's last theorem, and his proof failed because of that failure of the fundamental theorem of arithmetic not having been proven. But years later, it would be proven. And so that's one of the aspects with Fermat's last theorem and as to why we say that modern mathematics owes its development to that statement. And this is what we are going to be seeing for the next several lessons, is how Fermat's last theorem and the mathematicians that worked towards proving it developed the tools that would eventually become modern number theory and have applications not just in number theory but throughout math and in the real world when we count in cryptography. So now let us investigate the roots of unity further. And this is a result of Lagrange. And so keep in mind, so now this is 1772. This is following Lagrange's theorem. And even though Euler had already started working with these, Lagrange was the first to prove this factorization because it requires his result that we have used throughout our course. So namely, we have that the polynomial x to the n minus 1 for some natural number n factors out in the following way. And so the key thing here is, for the proof, is the following. So note that omega n to the j is equal to e to the 2 pi I over n to the j. So that's the definition of omega n, is just e to the 2 pi I over n. So now this here becomes e to the 2 pi I times j over n. But then if we go ahead and take omega sub n to the j and raise it to the n, this becomes e to the 2 pi I times j over n to the n, but exponent rules tells us that this here is just going to be 2 pi I to the j. By Euler's formula, we have cosine of 2 pi j plus I sine of 2 pi times j. So we have this here. But cosine of, now j is a natural number. So here, so I should have written this down for j, natural number. Since j is a natural number, we have that cosine of 2 pi times j is just always going to be equal to 1. And then sine of 2 pi j is always going to be equal to 0. So we have I times 0, so we just get back 1. So we have, so each omega sub n to the j is a root of x to the n minus 1. And moreover, for 0 less than or equal to j, less than or equal to n minus 1, the omega n's to the j's are distinct. And the reason for the distinction happens that now if we're restricting to j being between 0 and n, we're only going around the circle just once. And so we have all these quantities are going to be distinct over the complex numbers. So consequently, we have n roots, and by Lagrange's theorem, since we have those n roots, we now conclude that x to the n minus 1 is the product from j is equal to 0 to n minus 1 of x minus omega sub n to the j, since these are the roots here. And so we're done. We have now proven this lemma of Lagrange. So building on this lemma, we can prove the following statement. That now tells us if we choose any real number a, we have a factorization for x to the n minus a. So let's go ahead and see that. So what we are going to do, so we're going to go ahead, take x to the n minus a. We're going to factor an a out. But in doing so, we have x to the n over a minus 1. So we have this here. And now what we are going to do is write this here just slightly different. We're going to have x to the n, but now over, we're going to put an nth root of a, but now raising it to the n, so that's just going to be back a, so we have not changed anything. But now we have that this is just x over the nth root of a to the n minus 1. So we got this here. But we are back in this situation where now we have x to the n minus 1, where now this is our new x. And so by lemma 1.25.2, we get that this is the same as taking a of the product from j is equal to 0 to n minus 1 of x over the nth root of a minus omega n to the j. So we got this here. And now what we are going to do is bring in the a into the product. But what we want to keep in mind is that a is equal to the product from j is equal to 0 to n minus 1 of the nth root of a. So this is just the same, this is just a fancy way of saying the nth root of a raised to the nth power is equal to a. But doing so allows us to go ahead and write this as j is equal to 0, bring it in to each term in the product as an nth root of a. So we got this here. We now brought it inside the product, so we now distribute. And what we're going to get is that this is going to become x minus omega sub n j nth root of a. And that's what we wanted to prove, so we are done. And so we have a factorization now for x to the n minus A in general. Now, what if n were an odd natural number? Then we have very similar results. So let's go ahead. So observe that so here now we have x to the n plus 1. We want to show that this is equal to this product. So I'm only going to show this part over here. If we do the same argument we just did, we can prove this other statement. So let's go ahead and make the following observation. So if we take negative omega sub n to the j, and we raise it to the n, this is going to be equal, by exponent rules, negative 1 to the n, omega n to the j, and again, I keep forgetting to say that j is a natural number. So j is a natural, so we have negative 1 to the n, omega sub n to the j, to the n. But omega sub n to the j to the n, we have already shown that that's equal to 1. And so this is going to just be equal to negative 1 since n is odd. So for 0 less than or equal to j, less than or equal to n minus 1, omega sub n to the j is distinct. And thus, we have that by Lagrange's theorem, we get that x to the n plus 1 is going to be equal to the product we want. Since each negative omega n to the j is a root of x to the n plus 1. And so we're done with the first part of the corollary, and as I mentioned, if you run through the same argument we just did for x to the n minus a, then we can prove that x to the n plus a is equal to this right here. And to conclude today's lesson, we finish off with the equation of Fermat's last theorem. We have that if p is an odd prime and x, y, and z are natural numbers, then we have that x to the p plus y to the p is equal to z to the p. So that's our assumption. If that's the case, then we have this factorization. And so that's one factorization. We also have that x to the p is equal to z to the p minus y to the p, which is also going to be equal to the factorization we were looking at earlier, where now we go to p minus 1, and we have z minus omega sub p to the j times y. And so that's another valid factorization here. And so that concludes it for this lesson. So this is just a brief introduction to Fermat's last theorem, a topic that we will continue investigating further up from here to the last class. So the plan I have in mind for the coming lessons. So the next lesson will have us investigate Fermat's last theorem further, and we are going to prove Sophie Germain's theorem on Fermat's last theorem. And after that, we will end the course formally in the sense that there will be no additional content for homework, and that will give you time to work on your projects. But I will still be recording videos, and the plan for those videos is to give an outline of where we leave off with Sophie Germain's work in 1823, how that spearheaded the movement that eventually would lead to Kummer's proof in 1847 and the foundations of abstract algebra. And from there, we're going to continue that thread to see the development of mathematics over the years until we get to the actual proof of Fermat's last theorem in 1984. And so the talks are going to become more hand-wavy. I'm not going to be as rigorous as I tend to be in terms of proving every single statement. And so we're just going to take many things for granted since they are going to be beyond the scope of our course. But this is just to give you an appreciation of how these ideas developed over time to finally settle Fermat's last theorem. And in the process, understand why is it that we say that Fermat's theorem, that we owe the existence of modern mathematics to Fermat's theorem.